Thank you all for your love and support that you have shown in the end-to-end statistics series part 1 video that went live last Saturday at 6 p.m. IST. Welcome to this part 2 where we will be deep diving into some further topics. Just a recap, the previous part was all about the basics of statistics, basics of data, types of sampling techniques, probability, non-probability, and also we covered some descriptive analytics or descriptive statistics topic, especially IQR, mean, median, mode, and so on. In case you have not watched that video, recommend you to watch that. Link will be in the description. So welcome. This is the part 2. We are deep diving, and in this video, we are majorly going to focus on probability, different types of probability, different types of theory related to probability, cumulative, conditional, multiple other things, and also probability distribution. That includes Gaussian distribution and Poisson distribution and various other topics. So stay tuned. Please also share your love and support in this video and in the upcoming videos. If you have not subscribed the channel, please subscribe it, like and share this video. And I will also request you to post it on LinkedIn, tag me, so that it can reach to a wider audience. So let's get started. As I already told you, the agenda is very clear. In this video, 2 hours of video, we are focusing on the end-to-end probability and the different types of probability distribution. See you in the video. Hi, welcome to this module on statistics and the chapter on probability. In this video, we shall be discussing about the agenda of our next few videos. What are we going to cover in probability? We'll get started with probability in the next video, where we will talk about what exactly is probability, what are the probability related theories, concepts, and the formulas. Why do we use probability? Once that is done, we'll move into the additional rule of probability. And then we'll talk about the independent events. Further, we'll also talk about cumulative probability and conditional probability. And last but not the least, we'll be covering what exactly is Bayes' theorem. That's all about this particular video on this agenda. In the next video, we'll get started with the actual topics where we will start talking about probability and various concepts related to probability. See you in the next video. What exactly is probability? Probability denotes the possibility of the outcome of any random event. The meaning of this term is to check the extent to which any event is likely to happen. For example, when we flip a coin, imagine we are flipping a coin in the air. What is the probability of getting heads? Now, when we are tossing a coin, there are 2 outcomes that are possible. It could be either heads or it could be tails. Now, what is the probability of getting a head? The probability of getting a head is 1 by 2, which is 0.5. That means there are 50% chances of getting head and there are 50% chances of getting tails. So, the general formula of probability is number of favorable outcomes divided by the total number of possible outcomes. Now, in this example, number of favorable outcomes is when you are getting head, which is 1. How many total possible outcomes are possible? 1 and 2, which is 2. And hence, the probability here is 1 by 2. The probability is the measure of the likelihood of an event to happen. It measures the certainty of the event. So, if the trial is repeated number of times under homogeneous and identical condition, then the value of ratio of number of favorable cases to the total number of possible cases is called as probability. Now, when talking about probability, there are multiple scenarios, multiple keywords that we need to understand. Well, talking about probability, probability is something that always lies between 0 and 1. So, probability is always in between 0 to 1, which measure how likely an event to be occur. Now, let's try to go through some of the jargon, some of the keywords that we usually term or toss while considering probability. One of the terms is trial. What exactly is a trial? Trial is each performance in a random experiment. What is an event? Outcome of trial is an event, which is termed as P of E. Sample space, set of all possible outcomes in a random experiment. And then what is a random experiment? To perform more than once. Now let's try to understand these terms using some examples. The first question that we will consider is going to be, what is the probability of getting an even when throwing a single die? Everybody knows what a die is. When we throw a die, the possible outcomes are 1, 2, 3, 4, 5 and 6. Now this becomes your sample space because these are all your possible outcomes. The event here is going to be getting an even number. My bad, getting an even number. Okay, so the event is here getting an even number. Now what are the possible even numbers? 2, 4 and 6. Here, what will be the probability of this occurrence? Considering this as A, the probability of A will be, the formula is number of favorable outcomes divided by the total outcomes. What are my favorable outcomes? It's going to be 2, 4, 6, which is 3, divided by total outcomes, which is 6, which becomes 3 by 6, which is 1 by 2. So the probability of getting an even number in a single die is 1 by 2. Similarly, what is the probability of getting a multiple of 5? So the sample space remains same. Here the event becomes multiple of 5. What will be my A here? It will only be 5 because 5 is the only element here which is a multiple of 5. So what will be the probability of A here? It will be 1 instance out of 6 instance. So the probability of getting a multiple of 5 is 1 by 6. Multiple of 3, 3 and 6, which is become 2 by 6, which is 1 by 3. Now considering another example. What is the probability of getting an head when tossing a fair coin? Let me rub this off. Getting an head when tossing a fair coin. So when you are tossing a fair coin, the sample space becomes head and tail. The event becomes getting an head. The A becomes H. The probability of A becomes favorable outcomes by total outcomes, which is 1 by 2. Now, this was a very simple example. Let's try to take a complicated example. What is the probability of getting 2 heads while tossing 2 coins? Let's try to understand the sample space. The sample space will be either heads heads or heads tails or tails heads or tail tails. The event will be 2 heads. The A will be HH. And the probability of A will be 1 divided by 4. So almost 25% chances are there to get 2 heads while tossing 2 coins. So the probability is 1 by 4. In this video, we shall be talking about the addition rule of probability. In the previous video, we talked about probability. We also talked about some of the examples on how to solve a probability problem, on how to understand the concepts of probability by using tossing a coin or taking the die examples. Now, coming back to this video where we will be talking about the addition rule of probability. There are majorly 2 rules. rule 1 and rule 2. The first rule is when two events A and B are mutually exclusive, the probability that A or B will occur is the sum of probability of each event. Now, one example would be, imagine you are rolling a die. Now, the sample space of rolling a die would be 1, 2, 3, 4, 5 or 6. What if somebody asks you, what will be the probability of getting either 2 or 5? Obviously, there are two outcomes, right? So it will be 2 by 6, which will be 1 by 3. Now, using this formula, what will be probability of A? That will be getting a 2, which is 1 by 6. Probability of B, which will be getting a 5, which will be 1 by 6. And if you add both of them, 1 by 6 plus 1 by 6, this becomes 2 by 6, which becomes 1 by 3. So this is an example of additional rule of probability, rule number 1. So when two events A and B are mutually exclusive, so here two events are mutually exclusive, getting a 2 or getting a 5 are mutually exclusive. In that case, the probability, which is probability of A union B, becomes probability of A plus probability of B. There is a small terminology alert, which is union. What is this union operation? I'm expecting people to know about this, but just in case you don't know, union operation is nothing but, we'll take an example and try to understand. Imagine A is something, let's say 1, 2, 3 and 4. B is something, let's say 2, 4, 6 and 8. Now if we draw A and B, this is A and this is B. What are the elements that are common in both 2 and 4? So this comes here. What are the elements present in A not in B, which is 1 and 3? What are the elements present in B not in A are 4 and 8. Universal value A union B becomes the entire data set, which is 1, 2, 3, 4, 1, 2, sorry, not 4 and 6, 6 and 8, 6 and, my bad. So 1, 2, 3, 4, 6, 8. This becomes your A union B. A intersection B will be only this part, which is common in both, which will be 2 and 4. Okay, just wanted to explain this concept because this is a mathematical symbol, which basically means intersection. This means union. So here the probability of A union B will be probability of A plus probability of B. Talking about the second rule, when two events A and B are not mutually exclusive, the probability that A or B will occur is the sum of probability of each event minus the intersection of A and B. So your probability of A union B will be probability of A plus probability of B minus probability of A intersection B. Okay, this becomes your rule number 2. Now we'll take an example of both of these rules and try to understand. I think we already understood this example. I'll repeat once again. A single die is rolled. What is the probability of rolling a 2 or 5? There are two events happening, right? So there is a small mistake here. Please ignore that. So here the event of A occurring will be either 2 or 5. Okay. So the probability of A is getting a 2, probability of B is getting a 5. What will be probability of A? Getting a 2 will be only one instance, which will be 1 by 6. And probability of getting a 5 will again be one instance, which is 1 by 6. If you add them, this becomes 1 by 3, which we already understood in the previous slide. Now, talking about this question. In a math class of 30 students, how many students? 30 students. There are 17 boys and 13 girls. Okay. What is the probability of finding a girl from this? It will be 13 by 30. Clear? On a unit test, 4 boys and 5 girls made an A grade. How many made A grade? There were 9 students, 4 boys and 5 girls. What is the probability of choosing a girl or a A student? So what is the probability of girl or A student? This will become probability of girl plus probability of A minus probability of girl and A. Sorry, yeah, and A. What is probability of girl? Which will be 13 by 30. What is the probability of getting an A grader? There are 9 A graders out of a class of 30. So the probability of getting A grade is 9 by 30. A probability of getting not A grade will be 21 by 30. So we will consider this 9 by 30 minus girl and A. How many girl and A? Which will be 5. 5 girls and A graders. So 5 by 30. This becomes minus 5 by 30. The overall equation becomes 22 minus 5, which is 17 by 30. Because this scenario is where the event A and B are not mutually exclusive. That's all about this particular video on the addition rule of probability. In this video, we shall be talking about independent events. In the previous video, we talked about various probability concepts. Here, we were going to discuss about the independent events. What are independent events? Well, if there is a concept of independent events, there definitely would be a concept like dependent events. Simply, independent events refers to the occurrence of one event not affecting the probability of another event. When two events A and B are said to be independent if any of these following equivalent statements hold. P of A upon B is probability of A, probability of B upon A is probability of B. Generally speaking, this is what the multiplication rule of independence says. The probability of A and B occurring is going to be probability of A multiplied with probability of B. Two events A and B are independent if the fact that A occurs does not affect the probability of B occurring. Now, one of the classic examples. What if you are riding a bike? Another event is and watching a movie on laptop. Watching a movie on laptop. Now these are completely two different events and are independent of each other. Similarly, rolling a die and tossing a coin. These are definitely two different events. I'll try to frame a question so that we can try to solve this. The question is, what is the probability of getting an even number while rolling a die and getting a heads while tossing a coin? While you are rolling a die, the sample space, so this is your event A, now this is your event B. The sample space for event A while rolling a die is 1, 2, 3, 4, 5, 6. My event A getting even number is 2, 4 and 6. The probability of getting A here is 3 by 6, which is 1 by 2. In this case, the sample space is head and tails. The event A occurring, which is getting a heads, is 1. The probability of A or probability of B, let me write it as B so that we can reduce the confusion. Probability of B this will be B, probability of B will be 1 by 2. What is the probability of getting an even number and getting a heads together? So the probability of A and B, sorry, my bad. the probability of A and B. So the symbol here is going to be A and B. So the probability of A and B is going to be probability of A multiplied with probability of B, which is 1 by 2 multiplied with 1 by 2, which is 1 by 4. So probability of getting an even number and getting a heads is 25%. Because these two are independent events, they don't have dependency on each other. So one of the examples is that, as I told you, riding a bike and watching a movie on a laptop, studying hard for the exam and hitting six in cricket. They have no resemblance, they have no dependency. Studying hard or not is one event, hitting a six in cricket is another event, or scoring a goal in football is another event. Those are completely two different events and are called as independent events. In this video, we shall be talking about cumulative probability. By far, we already know what exactly is probability. Now, what is cumulative? The simplest definition of cumulative is something which is increasing or increased in quantity, degree, or force by successive additions. Well, cumulative probability refers to the likelihood that the value of a random variable is within a given range, and this range is defined here. Probability of x within the range of a and b. So here x is a random variable and a and b are the range limits. Sounds a little bit confusing, but let's try to understand using this example. Consider a coin flip experiment. If we flip two coins, what will happen? So considering the two coins to be fair coins, if we consider flipping two coins at a time or tossing two coins at a time, the sample space is going to be head head, head tail, tail head, and tail tail. These are the four possibilities while tossing two coins. Now, what is the probability that the coin flips would result in one or fewer heads? That means your output has to be at least one or fewer heads. Could be zero heads also. So zero head is this and one head is this. So definitely the probability becomes 3 by 4. But let's try to solve it using cumulative probability. The requirement is very clear. What is the probability that the coin flips would result in one or fewer heads? So of event X happening, one or fewer, less than or equals to 1. This is what we need to find out. And what is this? This is nothing but P of x equals to 0 plus P of x equals to 1. X equals to 0, that means 0 heads. That means one instance, 1 by 4. One head, that means two instance, which is 2 by 4. And now if I add it, it becomes 3 by 4. Now this is a typical example of cumulative probability. When somebody asks you something like this, can you tell me what will be the probability for getting one or fewer heads? Or if you are rolling a die, what is the probability that the addition of the number, let's say you are rolling two dice. If you are rolling two dice, obviously if you are rolling a single dice, these are the 6 entries possible, right? If you are rolling two dice, it could be 36 entries. 1 1 1 2 1 3 dot dot 1 6, again 2 1 2 2 dot dot 2 6, and it goes on till 6 6, right? What is the probability that the addition of both these numbers are less than equals to 5 or less than equals to 3 for simplicity? That means the addition of both the numbers could be 1, which is the minimum. The addition of two numbers could be 2, or addition of two numbers could be 3. Again, this is not possible, right? 1 0 or 0 1 is not possible. These are the two possibilities. X equals to 2 will be only one instance, which is 11. x equals to 3 will be 21 and 12. So there are 3 instances out of 36, which is 1 by 12, right? So this is an example of cumulative probability. In this video, we shall be talking about conditional probability. Simply, conditional probability is the probability of one event occurring with some relationship to one or more other events. The formula that we use in conditional probability is probability of B given A is true is nothing but probability of A intersection B divided by probability of A. Now, conceptually or formula wise, I think this should not be a difficult formula to memorize, but we'll try to take help of examples and see how this formula can be used in real life. There are some other rules of multiplication as well. Probability of A intersection B is probability of A given B is true multiplied with probability of B, or else other way around, probability of B given A is true multiplied with probability of A. Let's try to take an example, and without looking at the solution, let's try to solve it. An urn contains 6 red marbles, and 4 black marbles. Okay. 2 marbles are drawn without replacement from the urn. That means if you pick it, you cannot replace it. What if replacement is allowed? There are two chances, there are two possibilities. Let's try to talk about if replacement is allowed. That means the first ball could be red or black, and whatever it is, it goes back to the urn, and again the second ball is picked, which could again be red or black. So here the probability of getting a black is 4 by 10. Here the probability of black is getting 4 by 10. So if replacement is allowed, the possibilities of 2 marbles to be black would be 4 by 10 multiplied with 4 by 10, which is 16 by 100, which is 0.16. As without replacement is mentioned here, that means this is not a scenario. That means if I consider 6 red and 4 black, in the first pick there are two chances. It could be red, it could be black. What is the possibility of a black marble? It is 4 by 10 and this is 6 by 10. Right? If it is a black marble, then in the next pick, 1 is gone from here. So this becomes 3. So 3 by 9 is the possibility of black marble. So combined together, the chances of getting 2 blacks where replacement is not allowed will be 4 by 10 multiplied with 3 by 10, which will be 12 by 90. Again, you can just further do the decimal calculations. Now, this is something where we haven't used formulas, but looking at the formulas, we are actually following the conditional probability rule. Let's say the A is nothing but the event that the first marble is black. What will be the probability of A? It will be 4 by 10. Let B the event that the second marble is black. As replacement is allowed, here it will be 3 by 9. In the beginning, there are 10 marbles in the urn, 4 of which are black. So probability of A becomes 4 by 10. After the first selection, there are 9 marbles left. So 3 of which are black. So probability of B given A is true is 3 by 9. So using the basic rule of multiplication, the probability of getting black and black in the first pick and black in the second pick is this part. So this becomes this. Now take this one as an example. This is probability of B upon A is nothing but probability of A intersection B divided by probability of A. Simple, which is nothing but if it goes this way, So it becomes probability of A intersection B is nothing but probability of B given A is true multiplied with probability of A. So what is B given A is true? If A is true, that means somebody has already picked a black marble. In that case, what is the probability of B given A is true? This is 3 by 9 multiplied with probability of A. That means in the first pick, it has to be a black marble. So it becomes 4 by 10. So this becomes 12 by 90. So if you further simplify it, it becomes 0.133. So this is an example of conditional probability. Similarly, we'll take another example. In a group of 100 people, 40 bought sports drinks, 30 purchased snacks, and 20 purchased sports drinks and snacks. The question here is, if a buyer chosen at random bought a sports drink, what is the probability that they also bought snacks? Let's try to solve it line by line. Probability of A, which is buying a sports drink, is 40 out of 100, which is 0.4. Probability of A intersection B. A intersection B is nothing but the intersection of A and B, both happening together. It is also mentioned in the question. This will be 20 by 100, which will be 0.2. Now, using the mathematical rule that we discussed, we have to find if a buyer chosen at random bought A, which is bought a sports drink, what is the probability of buying snacks? So, probability of B given A is true, which is nothing but probability of A intersection B divided by probability of A, which is 0.2 divided by 0.4, which becomes 0.5. So the probability of buying snacks, probability that a person buys snacks given that he already has sports drink, is almost 50%. If we want to do the Venn diagram for this, let's say sports drink and snacks. We already know the numbers. This is 40, this is 20, and this is 30. So I hope everybody is clear. So if a buyer chosen at random bought a sports drink, what is the probability that they also bought snacks? So this is an assumption to be true. What will be the probability of this? So probability of B given A is true is going to be 50%. In this video, we shall be discussing about Bayes theorem. What exactly is Bayes theorem? Bayes theorem is an extension of conditional probability. Conditional probability, I hope everybody has already gone through the videos. Conditional probability helps us to determine the probability of A given B, denoted by P of A given B. Bayes theorem says if we know probability of A given B, then we can determine probability of B given A, or vice versa. So as we already know, probability of B given A is nothing but probability of A intersection B divided by probability of A. In other words, probability of A intersection B is nothing but probability of B given A is true multiplied with probability of A. So the formula of Bayes theorem is basically the probability of A upon B, or A given B is true, is nothing but probability of this divided by probability of B. And if I use this formula here, this becomes probability of B upon A multiplied with probability of A divided by probability of B. So this becomes my entire formula for Bayes theorem. Probability of A given B is true is nothing but probability of A multiplied with probability of B upon A is true divided by probability of B. That's all about Bayes theorem. Now let's try to take some examples and try to understand what exactly and how exactly we solve Bayes theorem problems. So let's say this is an example, a bag X contains 4 white and 6 black balls. So let me draw X contains 4 white and 6 black balls. While another bag Y contains 4 white and 3 black balls. One ball is drawn at random from one of the bags and it is found to be black. So the probability of finding a black object or a black ball from X is going to be 6 by 10 individually, and here it's going to be 3 by 7, which should be clear. Let's say you pick one of the balls from either of these bags and found to be black. Find the probability that it was drawn from bag X. Now this is an interesting question. Let E1 be the event of choosing bag. So E1 be the choosing event of choosing bag X. Similarly, E2 be the event of choosing bag Y. Then probability of E1 is nothing but probability of E2, right? So choosing a bag, it could be X bag or it could be Y bag. Probability of choosing individual bag is 1 by 2. Also, probability of A upon event 1 is true, is nothing but probability of drawing a black ball from bag X. Now this is 6 by 10. Similarly, the probability of A upon E2 is true. That means probability of black from bag Y is 3 by 7, which should be clear. By using Bayes theorem, the probability of drawing a black ball from bag X out of 2 bags. So probability of event E1 upon A is true is nothing but probability of E1 multiplied with probability of A upon E1 divided by probability of E1 multiplied with probability of A upon E1 plus probability of E2 multiplied with probability of A upon E2. This will be 1 by 2. Probability of E1 is 1 by 2 multiplied with E upon E1 is 6 by 10 divided by again 1 by 2 multiplied with 6 by 10 plus 1 by 2 multiplied with 3 by 7. This becomes 6 by 20 divided by, it becomes 6 by 20 plus 3 by 14. 6 by 20 plus 3 by 14. 6 by 20 divided by, let's try to solve this part. This will be, let's say 7 to 10, 70, 140. Let's say 140 in the denominator, 7, 6, 42. I could be minutely wrong, but I'm trying my best not to be wrong. So taking 140 in the denominator multiplied by 7, 6 multiplied with 7 is 72, and then multiply with 10, which is 30, which is 72 by 140. 72 by 140. This becomes 6 by 20 multiplied with 140 by 72. 0, 0 cancelled, 2 cancelled, 7, 6 cancelled, 12. So this becomes 7 by 12. So the probability that it was drawn from bag X is going to be 7 by 12. So that's all about this particular concept on Bayes theorem. It's a very important concept that will be used in many of your future topics as well. One of the most important theorems in the field of probability and statistics. In this chapter, we shall be focused on probability distribution. What exactly is probability distribution? In probability theory and statistics, a probability distribution is the mathematical function that gives the probabilities of occurrence of different possible outcomes for an experiment. It is a mathematical description of a random phenomenon in terms of its sample space and probabilities of events. For instance, if X is used to denote the outcome of a coin toss, in that case, the probability distribution of X would take the value of 0.5 for probability of X equals to heads and 0.5 for probability of X equals to tails, considering that the coin is fair. Examples of random phenomena include the weather conditions at some future date, height of a randomly selected person, the fraction of male students in a school, the results of a survey to be conducted, etc. etc. There are many types of probability distribution. In this particular session, in this particular chapter, we shall be talking about each one of them. We'll get started with uniform distribution. Then we will talk about binomial distribution, Poisson's distribution, and normal distribution. At the last class, we will also talk about some of the feature scaling techniques, and we will see how scaling can be done for normal distribution and how can we convert a normal distribution to a standard normal distribution. So these are the topics that we will be covering in this particular chapter. See you in the next video where we will be jumping into each one of them. In this video, we shall be talking about uniform distribution. Now, what exactly is uniform distribution? Simply, in probability theory and statistics, the continuous uniform distribution or rectangular distribution is a family of symmetric probability distributions. Majorly, uniform distribution is of two types: discrete uniform and continuous uniform. Let's try to understand each one of them, and then we'll probably take an example and help you out. In layman's term, each integer value between A and B has the same possibility to happen. Everybody knows the meaning of discrete and continuous variables. So if we know what is discrete and what is continuous variable, then understanding this concept won't take that much of time. In simple terms, the probability of X happening is 1 by n. Take an example of throwing a dice. When you throw a dice, let's the event be throwing a dice. When you throw a dice, what will be the sample space? The sample space will be, it could be anything, 1, 2, 3, 4, 5 and 6. What is the probability of getting 1? It is 1 by 6. Probability of getting 2, 1 by 6 and so on. So in short, the probability of getting each and every number is individually 1 by 6. If I start drawing, you will probably end up a diagram like this, where A and B are your events. It could be 1, it could be 2, it could be 3, 4, 5 and 6. Imagine there is another line for 5. And in your y-axis is always your probability of X, which is 1 by n. In this case, the n is 6. So this value is nothing but 1 by 6. That is your discrete uniform distribution. Now, what exactly is continuous uniform distribution? In layman's term, any values, integer or decimal values, between A and B has the same possibility to happen. The only difference between discrete and continuous is that here you only have the discrete values. Let's say there is something like this. Here you only have discrete values. What is the probability of 2? The probability of 2 will be 1 by 6. What will be the probability of 4? It will be 1 by 6. Can we have a number like 2.5 or 3.4? What is the probability of getting 3.4? Not possible, because 3.4 itself is not a part of the sample space because of the discrete nature of the data. So in continuous uniform, it could literally be any number. In layman's term, any values, integer or decimal values between A and B has the same possibility to happen. So now let's say we have a number A and we have a number B, and the data is continuous data. So what will be the probability? The probability, I'm talking about continuous, the probability of X lying between A and B is basically 1, right? This entire box is going to be 1. The probability is going to be 1. That means if there are n number of continuous objects, you can imagine each probability accumulated value will be 1, right? Each probability value will be like 1 by something, and accumulation of each continuous variable ultimately will lead to 1. So this statement holds true, right? Now as you can see, if I name it something like A, B, C and D for an example, this becomes a rectangle. What will be the area of this rectangle? The area will be height multiplied with length. So area becomes height multiplied with width or length, right? So what will be height? What will be the length? The length will be b minus a. B minus a. And we already know that the entire area is 1. So height multiplied with b minus a is 1, which means height is equals to 1 by b minus a. And that is the reason we have mentioned here the height as 1 by b minus a. Simple. In this case, in continuous uniform distribution, the mean is usually a plus b by 2, which is similar to your median as well, which is somewhere here, right? Imagine there is a scenario, for example, I'll try to rub this off, and probably let's say somebody asks you what is the probability of falling between C and D. So what will be the probability of falling between C and D? It is nothing but height multiplied with length. What is the length? It is D minus C. D minus C. What is height? Height is going to be constant, 1 by B minus A. So 1 by B minus A. So the probability here will be D minus C divided by B minus A. Usually in the case of uniform distribution, as I already told you, mean is nothing but A plus B by 2, which is similar to your median, and your standard deviation is nothing but square root of B minus A square divided by 12. That's all about uniform distribution. Let's go ahead and talk about an example which we already discussed. So if you are rolling a die once, the probability of each of the possible outcomes, that is 1, 2, 3, 4 or 6, is even, which is 1 by 6. The probability of getting 1 is 1 by 6. Probability of getting 2 is 1 by 6. So the probability is constant of whatever values you pick from the sample space. So this is how your uniform distribution looks like. For each and every value from 1 to 6, the probability is 1 by 6, which is almost 0.8, 0.18, I think. If I talk about 1 divided by 6, 0.17. 0.17, right? Almost close to 0.2. And this is throughout 0.17, 0.17, 0.17, and so on. In this video, we shall be talking about the binomial distribution. What exactly is binomial distribution? The binomial distribution is a probability distribution used in statistics that summarizes the likelihood that a value will take one of two independent values under a given set of parameters or assumptions. The underlying assumptions of the binomial distribution are that there is only one outcome for each trial, that each trial has the same probability of success, and that each trial is mutually exclusive or independent of each other. Let's try to understand binomial distribution using a small example. Imagine you are tossing 5 coins. Obviously, when you toss a coin, the outcomes are head or tails. So imagine you are tossing 5 coins. So how many outcomes will be there? Let's say all 5 heads, or it could be 5 tails. It could be 3 head and 2 tails. It could be head, tail, head, tail, head, and it could be many other combinations. In short, there will be 32 combinations that are possible while you toss 5 coins. How is that possible? For the first coin, the possibilities are 2 times. Either it is head or tails. For the second coin, again the possibilities are 2, and it goes on till the fifth coin, which becomes 2 to the power of 5, which is nothing but 32. So if I talk about the sample space, I cannot write down, but there are 32 sample spaces, like 32 times. It could be combination of HTT, HT, HT, HHT, HHH, HH, TTT, something like that, right? Now, let's say my X here is finding the number of heads. What if I want to have what is the probability of finding 0 heads? Finding 0 heads, there is only one scenario, which is TTT, which is 1 out of 32. So probability of X equals to 0 is going to be 1 out of 32. Let's try to go to the next page and try to do a writing here itself. So I'll quickly write down again. My X here is number of heads, and I'm tossing 5 coins. So what are the total probability? The possible outcomes is nothing but 2 multiplied with 2 multiplied with 2 multiplied with 2 multiplied with 2, which is 2 to the power of 5, which is 32. These many possible combinations, right? Now, what is probability of X equals to 0? That means when you have 0 heads, so that's only one case, right? If all the coin are having tails, tail, 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 which is 1 out of 32 instances, right? Formula wise, it is nothing but 5C0 divided by 32. What is 5C0? 5C0 is simply 5 factorial divided by 0 factorial multiplied with 5 factorial multiplied with 1 by 32, which is 5 factorial cancel, 0 factorial is 1, which becomes 1 by 32. Similarly, let's say you ask me what is the probability of getting one head. Now it could literally be this H T T T T, or it could be T H T T T, or it could be T T H T T. It could be H here or it could be H here. Literally there are 5 combinations: T T T H T and T T T T H, right? There are 5 combinations. which should be 5 by 32. Using formula, we will just use n c of x, which is 1, divided by 32, which is 5 factorial divided by 1 factorial multiplied with 5 minus 1 factorial multiplied with 1 by 32, which is 5 factorial divided by 4 factorial multiplied with 1 by 32. 1 factorial is always 1, 5 minus 1 factorial is 4 factorial. So what is 5 factorial? 5 factorial is simply 5 into 4 into 3 into 2 into 1, and 4 factorial is 4 into 3 into 2 into 1 multiplied with 1 by 32. Everything is cancelled, 5 remains, which is 5 by 32. Similarly, if you go ahead for p x equals to 2, 5c2 divided by 32, which is 5 factorial divided by 2 factorial, 3 factorial into 1 by 32. 5 factorial, 3 factorial cancelled out. It remains with 5 cross 4. 2 factorial gets cancelled out here. So it becomes 10 by 32. Similarly, px equals to 3 will also be 5c3 by 32, which is again 5 factorial divided by 2 factorial, 3 factorial into 1 by 32, which is again going to be 10 by 32. And probability of x equals to 4 is again going to be 5 by 32, and probability of x equals to 5, that means all the 5 cases it has to be heads, which is going to be 1 by 32. Simple. Now that's all about the 5 different combinations of getting the number of heads. If I use this technique and start plotting, so let's say this is my 10 by 32, let's say this is my 5 by 32, 1, 2, 3, 4, 5, and this is 1 by 32, right? So 0, 1, 2, 3, 4, 5. So at x equals to 0, it's going to be 1 by 32. At x equals to 1, it is 5 by 32, something like this. And then it is 10 by 32, and then again 10 by 32, and then this, and then this, something like this, right? This is how the graph looks like. And this is your binomial distribution. If I quickly draw this diagram like this, it was not that accurate, but somehow, let me just redo it. Something like this, right? Now this graph is nothing but a normal distribution graph. Like it looks like the bell curve, right? Normal distribution. But normal distribution is usually meant for continuous data. Here we are analyzing discrete data. 1, 2, 3, 4, 5. These are discrete data. So in short terms, binomial distribution is nothing but a version of normal distribution for discrete data. For continuous data, we call it as normal distribution. So definitely we'll have a class on normal distribution to understand more about it. But this is how your binomial distribution looks like. The internal graph which has been formed up looks similar to a normal distribution or a bell curve. The formula of binomial distribution is pretty much clear. The probability of x is nothing but n c of x, p to the power of x multiplied with 1 minus p to the power of n minus x. Okay, so we'll take another example and we'll try to solve it using this formula, because here I have somehow used this formula, but it's not quite visible because it was a simpler example of 5 coins. We'll try to take a difficult example and try to implement this particular example and to implement this particular formula. So talking about this example, a coin is tossed 10 times. What is the sample space? 2 to the power of 10. Imagine whatever it is. 2 to the power of 5 is 32. 64, 128, 256, 5, 112. It should be 1024. If I am not wrong. 1024. This is my sample space. These many combinations are possible. Let's not go into that direction. What is the probability of getting exactly 6 heads? So we need to find probability of x equals to 6. Here x is getting a head. Simple. X is getting a head. We want to find probability of x equals to 6. How many trials do we have? The n value is here 10, right? X value is 6. Simple. What is the probability of success? That means getting a head. Probability is 0.5, which is 1 by 2. Probability of failure is q, which is again 1 by 2. Using binomial distribution, we'll try to use this formula. N C x p to the power of x 1 minus p to the power of n minus x, which becomes 10 C 6, 0.5 to the power of 6, 0.5 to the power of 4, which becomes 10 factorial divided by 4 factorial multiplied with 6 factorial multiplied with 0.5 to the power of 10, in short, right? If you try to solve this, 10 factorial, 6 factorial cancelled out, which should be left out with 10, 9, 8, 7 divided by 4, 3, 2, 1 into 0.5 to the power of 10. It gets cancelled out. 2, 3 gets cancelled out. 3, 2 gets cancelled out. 5. So 5 into 3, 15, 230 into 7, 210 multiplied with 0.5 to the power of 10. If you go ahead and calculate it, you will probably land up this number, which is 0.2. So the probability of getting exactly 6 head is 0.2. I hope everybody is clear with this formula. It looks very complicated, but it is very simple. NCX is nothing but n factorial divided by n factorial, divided by x factorial multiplied with n minus x factorial. This is what it is meant by this one. That's all about this particular session on binomial distribution. And in this video, we shall be talking about Poisson distribution. Poisson distribution is a type of probability distribution. In fact, it is a discrete probability distribution. The discrete probability distribution of the number of events occurring in a given time period, given the average number of times the event occurs over that time period. Let x be the discrete random variable that represents the number of events observed over a given time period. Example, calls per hour at a call center. Let lambda be the expected value or the average value of x. Example, the average number of calls received in a call center is 10. So your lambda value is 10. If x follows a Poisson distribution, then the probability of observing x events over the time period is this. Probability of x equals to x, lambda to the power of x multiplied with e to the power of minus lambda by x factorial, where e is nothing but your Euler's number, which is 2.718. Let's go ahead and take an example. We'll take the same call center example. The average number of calls for a call center per hour is 10. So lambda equals to 10. The probability of having different number of calls in an hour could be calculated as this. The probability of 0 calls, following the same formula, lambda to the power of x e to the power of minus lambda by x factorial, we will replace the x value as 0 and lambda value as 10. If you replace, you are going to get the probability value as 0.0045%. If you want, you can keep on doing for 1 call, for 2 call and so on. Arbitrarily, I have done the probability for 3 calls. Again, using this formula where lambda is 10 and x is 3. And if you replace these values, the value is coming as 0.75%. And you can see there is a steady increase in the probability value till 10 or 11 calls. What will be the probability of getting 20 calls? X equals to 20. I will use the same formula, lambda to the power of x, which is 10 to the power of 20, multiplied with e to the power of minus 10, divided by 20 factorial. Now if you go ahead and use a calculator and calculate this value, the value is going to be almost 0.001, which is around, if you multiply 100, which is around 0.1%, almost. So this is how your Poisson distribution looks like. So probability of 0 calls is here, probability of 1 call, 2 call, and you can see the probability keeps on increasing till a certain extent, and then again it started decreasing. And this is the property of Poisson distribution. In this video, we shall be talking about normal distribution. What exactly is normal distribution? Well, before getting into the topic, let's try to talk about the other names of normal distribution. Normal distributions is also called as Gaussian distribution. And as the distribution looks like this, it is also called as Bell's curve. It looks like a Bell's curve. So normal distribution, also known as the Gaussian distribution, is a probability distribution that is symmetric about the mean, showing that data near the mean are more frequent in occurrence than data far from the mean. Graphically, normal distribution looks like a bell curve, as I already mentioned. And it is important in statistics and is key to the central limit theorem. What exactly is the empirical rule? The empirical rule basically tells us that if this is how our normal distribution looks like, for all normal distributions, 68.2% to be very precise, but let's assume 68%, almost 68% of the observations will appear within plus or minus 1 standard deviation of the mean. What does this mean? Normally, in a normal distribution, the center is usually the mean value. What is mean value? Mean is simply the average of all the numbers that we have. If I have 1000 records, and if let's say I'm analyzing age, that means for all these 1000 records, whatever mean I will have, that is this. Again, on these 1000 records, let's say I want to calculate the standard deviation, which we already studied in one of our previous classes. Standard deviation is nothing but, the formula of standard deviation is summation of xi minus mu square divided by n. And usually this formula is for population data. And obviously the denominator becomes n minus 1 for sample data. We already covered all these concepts. I hope it's kind of a refresher to you right now. Now, mu is calculated, sigma is calculated. Usually this is your mu. This is usually your mu plus sigma and mu minus sigma. And it is told that the total percentage of data in this particular area is around 68%, 68.2% to be very precise. Similarly, if I start plotting mu plus 2 sigma and mu minus 2 sigma, usually this range is 95.4%. 95.4%. You can see, we'll try to ignore this image and let's try to focus on this image. This is your mu. Mu minus sigma, mu plus sigma. What is in this range? 68.2%. Mu minus 2 sigma, mu plus 2 sigma. What is in this range? Is 95% of the data. Mu minus 3 sigma, mu plus 3 sigma, 99.7% records. Now, as per normal distribution, it says that if the data is following the normal distribution, that means 68% of the data lies between mu plus minus 1 standard deviation. 95% lies between mu plus minus 2 standard deviation, and 99.72% of the data falls within plus minus 3 standard deviation. What happens to the 0.03%? My bad. What happens to the 0.3%? Because 100 minus 99.7 is basically 0.3. What happens to this 0.3%, which is usually beyond this line and beyond this line? Now this 0.3 percentage of the data is called as outliers. People also call it as anomalies. These are outliers. So if your data is following normal distribution, it is very easy for us to understand the outliers in the data. Now, how do you treat your outliers is a different story. But this is all about the empirical rule. There are different jargons, different words that we use. Mu plus minus 1 standard deviation is also called as 1 sigma. Mu plus minus 2 is also called as 2 sigma. Mu plus minus 3 is also called as 3 sigma. So sometimes when you hear what is 3 sigma rule, or what is empirical rule, or what is the normal distribution rule, do not panic. All are same. Normal distribution or Gaussian distribution. Bell-shaped probability distribution. Most of the numbers are mid-range with less extreme values. Example 1, most people get mediocre score while small number of people get low score or high score, which is quite obvious. Whenever we have examination in our school days, majority of the people, I'm not it depends from exam to exam, from chemistry to English to mathematics, but the general idea is that majority of the people lies between this range. The range could be like 50 to 70, we don't know, and this could be the low marks and this could be your high marks. So another example is most people have an average height, but small number of people are extremely tall or short. Normally distributed data follows the 1 2 3 rule. Again, one more keyword. As I told you, 3 sigma rule or empirical rule or 1 2 3 rule, all are same. This rule states that there is a 68% probability, which is this one, 68.2 very precisely, almost 95% within this range, and 99 within your plus minus 3 standard deviation, 99.7 to be very precise. They lie between your 3 standard deviation of the mean. Now, if you want to take some examples and try to solve this, probably you can do that. For example, let's say I have 10 students. I will write it down, students. Students marks, let's say mathematics marks. One of them has got 40, one of them has got 60, 65, 70, 75, 80, and one of them has got 72, 74, 70, 68, 92, 89, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 records. Sorry, 12 records. Now, based on these 12 records, we'll try to calculate the mean standard deviation and see how many data points are falling within plus minus 1, 2, and 3 standard deviation. Obviously, like to get the exact amount of 68 values, at least you need 100 records, right? Now, if you take 10 records, either 6 or 7 records would be falling in this range logically if the data is normally distributed. It cannot be 6.8, right? There cannot be 6.8 people falling under that category. So in order to have a concrete value, either you take a larger sample, or if you're taking a smaller sample, just adjust with the decimal places, right? Something like that. Now let's try to calculate the mean here. What will be the mean here? We'll try to calculate 40 plus 60, 100 plus 65 plus 70 plus 75 plus 80 plus 72 plus 74 plus 70 plus 68 plus 92 plus 89, which is 855. 855 divided by 12, which makes it 71.25. Similarly, standard deviation. Again, what I will do is I'll try to take help of one of the online tools, or you can simply take help of your formulas. Standard deviation is nothing but summation of square root of xi minus mean square by n. Okay, let's try to take the traditional approach. So what I'll do is I'll probably create a, we'll try to create a new page. So I have created a new page. Here, let me write down all the data points that I have. Now I realize that I should have taken a simpler example. Let's say 40, 60, 65, 70, 75, 80, 72, 4068, 72, 74, 068, 92, 89, 92 and 89. So what will be x minus mu? Imagine we are kind of rounding off the mu value. Let's say we'll consider 71. Okay, we'll round off the marks. The mu is 71. So what will be x minus mu? Minus 31, minus 11, minus 6, minus 1, 4, 9, 1, 3, minus 1, minus 3, 21, 18. I could be wrong, but I'm pretty much sure I'm not wrong. So x minus mu square, 31 multiplied with 31. It is 961, 121, 36, 1, 16, 81, 1, 9, 1, 9, 441, and 324. 21 into 21 is 441. Correct. Now what I will do is I'll try to add these numbers, because what we are doing is summation of xi minus mu square divided by n and then root over. This is what we are trying to do. So what is the numerator part? This part, the summation of all these things. So if I start calculating, 961 plus 121 plus 36 plus 1 plus 16 plus 81 plus 1 plus 9 plus 1 plus 9 plus 441 plus 324, 2001. Wow, great number. 2001 divided by 12, root over, divided by 12, which is 166.75 root over, which comes around 12.9. Again, we'll round off, make it 13. Now my mu is 71. My standard deviation is 13. Let's try to draw it. And right now itself, we will try to come to a conclusion whether our data is normally distributed or not. So the mean value is 71, plus 1 standard deviation is 84, plus 2 standard deviation is 97, plus 3 standard deviation is 3910, minus 1 standard deviation is 58, minus 2 standard deviation is 45, minus 3 standard deviation is 32, right? Now how many data points are lying between the first and the, like in this range, how many data points are lying? 40 is not lying, this is lying, 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 lying. That's it. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 records. How many are within this range? Within 45 to 97, this. We have 11 records. And within this range, we have 12 records. So how much percentage do we have here? So if you calculate the percentage, 9 divided by 12, around 75%. Around here, we have 11 divided by 12, which is 91.6%. And around here, we already have 100%, which means there is no outlier in this particular data. It is somehow following normal distribution, but with no outliers. What if we had outlier? Maybe somebody, okay, somebody's score cannot go beyond 100 marks, but let's say somebody's score is less than 32. Maybe somebody is 16. Again, all these calculations will change here, right? The standard deviation calculations will change. So all these numbers will also change. You can do this activity, but this is how things work. This is how we usually do our normal distribution. Now, one question in our mind could be, do we deal with, I'll try to change the question, the data that we analyze on a daily basis as a data analyst, do we really care about normal distribution? Is our data actually normally distributed? No, the answer is going to be no. Normal distribution is a very hypothetical scenario which rarely exists. Now, if it rarely exists, why do we even are learning about this concept, because this is a very hypothetical concept. It is an ideal scenario. If the data is normally distributed, then it creates a lot of it gives you a lot of uh, opportunity to understand the data and do the analysis properly. A lot of data, almost 99.99% of the real time data, are never normally distributed. What if you get data which is not normally distributed, which is not like this, which could be like this, or which could be like this, or which could be like this? Now this is not normal distribution. What will you do with this? Now these are some scenarios which is called as skewness. There are some scenarios like skewness, scenarios like kurtosis, which is quite normal in any kind of data. If you encounter these kind of scenarios, either you convert the data to normal distribution or you deal with it, right? So in our next classes, we'll also talk about some concepts like skewness and kurtosis, and then I will also talk about some of the transformation techniques that we usually use to transform those kind of data that are overly skewed, highly or lowly skewed, like positively or negatively skewed, and try to convert the skewness data to a normally distributed data. That's all about this particular topic on normal distribution. I hope your concepts are clear. In the next video, we shall talk about skewness and kurtosis. See you in the next video. Bye bye. In this video, we shall be talking about skewness. In the last video, you understood about the normal distribution, which is the Gaussian distribution and is also called as the Bell's curve. We understood that in a normal distribution, mean is usually the midpoint of the values of the records, and then we have mean plus minus 1 standard deviation, plus minus 2 standard deviation, plus minus 3 standard deviation. We also learned about the empirical rule, which basically says that 68% of the data falls between the first 1 plus minus 1 standard deviation. Almost 95.4% of the records within the plus minus 2 standard deviation, and 99.7% data in the plus minus 3 standard deviation. What happens to the 0.3% data which is beyond this are basically called as the outliers. Now this is one of the generic scenarios. This is a very hypothetical scenario that we usually come across when we get started with the data analysis activities, when we start analyzing certain features, certain columns in a real day-to-day activity. We usually don't find any kind of data to be normally distributed. Now there are so many problems with the data. Now when we talk about problems, and that is where we are talking about skewness. What is skewness? Skewness measures the distribution of the data. It indicates whether the data is distributed symmetrically or not. If it is symmetric, then it is normally distributed. This is symmetric data. Data is evenly distributed on the left side, evenly distributed on the right side. If the data is not evenly distributed, then the different types of skewness are positive skewness and negative skewness. Now look at this graph. Here the data is not uniformly distributed, not uniformly, sorry, not, I would say, not symmetrically distributed, right? You can see there is a hump on the left hand side. Here there is a hump on the right hand side. Normally in normal distribution, your mean, median and mode is your central line. But in this case, in the right skewed, you can see mode is here, median is here and mean is here. So this type of scenario is called as right skewed. And when you see this kind of scenario, then it is called as a left skewed. These are the two different types of skewness. Now, the question that might be coming to your mind is, let's say we started analyzing data and we got that our data is right skewed or left skewed. How to fix that problem, or how to convert it into normal distribution? Well, there are a lot of transformation techniques. So some of the transformation techniques includes logarithmic transformation, square root transformation, cube root transformation, In case of some other scenarios, we might go for the square transformation. That means converting the data into the square format. Cube transformation, reciprocal transformation. So there are so many techniques that we usually do with the data, and then check their skewness score, whether their skewness score is within the range of 0 or not, like nearby 0 or not. In that case, we can assume that it is somehow in a better shape, somehow closer to the normal distribution. Well, the only problem now is all these kind of transformation techniques will need you to understand about pandas and numpy as well, which is going to be covered in one of the next modules. So what we will do is we'll try to take a pause here, try to understand this way. If your data has skewness, then it has to be transformed. How to transform using Python, pandas and numpy, we'll try to explain that in some of our future videos, in that either in that module or probably when we jump into the EDA sessions. In that class probably we'll talk about these things. That's all about skewness. In the next video we shall be talking about kurtosis. See you. In this video we shall be talking about kurtosis. Like the way we discussed about skewness in the last video, kurtosis simply means it measures the thickness of the distribution of data. The degree of tailedness of the data is measured by kurtosis. Kurtosis usually tells us the extent to which the distribution is more or less prone than the normal distribution. What are the different types of kurtosis? The normal distribution is basically called as meso. It is basically called as mesokurtic. Platykurtic is the red graph that you are seeing. It looks like a normal distribution, but you can see that it is somehow fat in this portion, right? Like larger number of data points are around here. Same with green, also following a similar pattern like normal distribution. The data is symmetrically distributed. The number of records here is very similar to the number of records here, but you can see that in this area less number of records are available. So kurtosis and skewness are completely different concepts. Skewness is all about the symmetric nature, but kurtosis maintains the symmetric ability. It is symmetric in nature, but you can see the issues. Issue is with the distribution of data. Now, if we identify these kind of scenarios, if we identify that we have a leptokurtic distribution or a platykurtic distribution, in that case also we go for the similar kind of transformation that we learned in the previous class. The transformations include log transformation, reciprocal transformation, square root transformation, cube root transformation, and so on. So that's a basic understanding on kurtosis. That's all about kurtosis. Probably once we learn about the pandas, numpy and the Python part, we will definitely come back to this topic and try to help you out on how practically we can solve these problems, how to solve the skewness problems and how to solve the kurtosis problems using Python code. That's all about this particular video. See you in the next video. Bye bye. In this video, we shall be calculating probability with z-score for normal distribution. But before getting into z-score, let's try to understand what exactly is normal distribution and what is standard normal distribution. Normal distribution is somehow understood from some of our previous videos. You can see the left screen is basically the normal distribution, and this is how a data is distributed normally. Normal distribution, which is also called as Gaussian distribution or which looks like a bell curve. You can see the middle point of this graph is your mu, which is nothing but your mean value. Similarly, you have your mu plus minus 1 standard deviation, mu plus minus 2 standard deviation, and mu plus minus 3 standard deviation. And we all know that Within the first standard deviation, which is mu plus minus 1 standard deviation, almost 68% of the data lies. Between 2 standard deviation, almost 95.4%, and within 3 standard deviation, almost 99.7% data lies. What happens to the 0.03%, which is beyond this graph? Those are basically your outliers. And this is the scenario when it comes to normal distribution, which is a hypothetical scenario. Not all type of data will have a distribution like this, but the data that is following normal distribution, they will only be having distribution like this. Now, normal distribution is understood. What exactly is standard normal distribution? Before talking about standard normal distribution, let me talk about a concept called as feature scaling. Feature scaling. Feature scaling is a very important aspect in the field of predictive analytics, in short, in the field of analytics and data science. Now just imagine you have a height and you have weight. Let's just talk about height and weight. Simple. Let's say some of the customers' data that I have is, let's say, my bad. Some of them as having 170, 170, 160, 180. These are the different heights of people: 70 kg, 75 kg, 65 kg, and 80 kg. Now you can see both these height and weight are in different scale. One is in a hundreds format and one is in a tens format. Now what we do is we perform feature scaling on these raw data. The reason of feature scaling is we usually perform feature scaling so that all the variables, all the features like height, weight, and all the features that you are analyzing from a particular set of data comes into a certain scale. Now, why do we need to scale down the values? Because ultimately your data will be passed to a predictive model, to a predictive analytics model, which is otherwise called as a machine learning model. And in that particular model, you have to scale down the values. You have to get it in the scale of 0 to 1 or probably -1 to 1, which is a more readable format by the computers, because ultimately you're passing the data to a computer program, right? So feature scaling is an important aspect, and when it comes to feature scaling, two of the most important techniques is standardization and the second one is normalization. Now when it comes to standardization is simply nothing but the new data is going to be x minus mu divided by sigma. And normalization, the new data is going to be x minus x minimum divided by x maximum minus x minimum. Now in this case, we are applying the standardization technique to kind of do the feature scaling on the raw data. Now we'll try to use this example, use this formula for standardization, which is z equals to x minus mu by sigma. Mu being the mean and sigma being the standard deviation. Let's try to calculate few things. We will try to calculate the z value where mu equals to mu, x equals to mu in this particular case. Now in this case, my z value will be x minus mu by sigma, which is x is going to be mu. So mu minus mu by sigma, which is going to be 0. And that is the reason the z value is 0 here. What will be the z value here? Mu plus 2 sigma. Z value is going to be x minus mu by sigma. I will replace x with mu plus 2 sigma. So mu plus 2 sigma minus mu divided by sigma. Mu cancel. 2 sigma by sigma is going to be 2. So the z value is 2. So as per this particular values, when you are converting into the standardization format, or creating the standard normal distribution, the new points in your x-axis is going to be 0, 1, 2, 3, minus 1, minus 2 and minus 3, and these are called as your z-scores. The formula of which is already discussed, which is x minus mu divided by sigma. So if you want to find the probability, first step is to find out how far the value of x is from mu in terms of number of standard deviation. The number is named as z-score or standard score or z-value. Basically, it tells you how many standard deviations away from the mean your random variable is. I hope everybody is clear with this thing. Let's try to also calculate the z-score at here and here. The z-score at here will be z equals to x minus mu by sigma. X is mu minus 3 sigma. So mu minus 3 sigma minus mu by sigma. Mu cancel. Minus 3 sigma by sigma. Sigma cancel. It's going to be minus 3. And that is the reason the value here is minus 3. So what only changes from this to this is the z-score. That's it. That means this is the standardized format, or this is the feature scaled format. The values has been scaled down, and the values that you see on the x-axis are your new values instead of mu plus sigma, mu minus sigma, and these values are called as z-score. The distribution in z-score, the distribution in standard normal distribution remains the same. It is still 68%, it is still 95%, and it is still 99.7%. That means if somebody asks you what is the percentage of data falls between a z value of plus and minus 1, then it remains the same. It's going to be 68%, which is the same here. Mu plus minus 1 standard deviation. That's all about this particular video. In the next video, we shall be talking about the examples of this particular topic. Hi, in this video, we shall be focusing on Z table. On your screen, what's visible is basically called as a Z-score calculation table, or simply a Z table. On the left hand side, you will probably see various Z values ranging from negative values from minus 0 to minus 1.99. This basically refers to minus 1.99. Similarly, this table is all for the positive Z values, starting from 0.00 to 1.99. Now, let's try to take an example and see how to use this particular table. So one of the examples is, just imagine there are 200 participants or applicants who have taken a statistics test. 200 people that have taken statistics test. Mr. John has basically got 700 score out of 1000. Simple. The average score was 600. So my mu value is going to be 600. And the standard deviation was 150. So sigma is 150. Now we would like to know how well John performed compared to his peers. So we need to standardize his score. That is, calculate a z-score corresponding to his actual test score, and use a Z table, which is this table, to determine how well he did on the test related to his peers as compared to his peers. In order to derive the z-score based on the information that we have, we will be using the formula z equals to x minus mu by sigma, which is nothing but, my x is nothing but the score that John has got, which is 700, minus mu, which is 600, divided by 150, which is 100 by 150, which is almost 2 by 3, which is 0.666666. If you round it off, it will become 0.67. Now, for Z value 0.67. Now, in order to figure out how well John performed on the test, we need to determine the percentage of his peers who go higher and lower scores. That's where your Z table comes into picture. If you noticed, there are two Z tables, one with the negative values and one with the positive values. If a Z score calculation yields a negative standardized score, refer to the first table, otherwise refer to the second table. As the Z score is positive, so the left table is out of scope. We will be focusing on the right table. So what we will do is we will try to see 0.67. So 0.6 is here, 0.60, 0.61, 0.62, 0.63, 0.64, 65, 66, 67. So at 0.67, my value is 0.7486, which is basically nothing but 74.86%. This means that almost 75% of the students scored lower than John, and only around 25% of the students have scored more than John. So if I talk about the real percentage, as we have 200 students, the final outcome or summary is basically that 75% student out of 200, 75% of 200 is basically 150. That means John did better than 150 students. And that is how you see your Z score table. I hope that was informative. In the next video, we shall be taking another example and see how to solve this particular problem related to Z score. See you in the next video. Bye-bye. Hi. Let's take another example related to this topic. We will be taking an example of height distribution in a class. Imagine you are doing a study on the height of a class of university students. Assuming that the height is following a normal distribution. Let's say the height is following normal distribution. What is the percentage of students who are shorter than 1.5 meters? That's fine. Let's say we'll try to draw this again. Imagine the data is following normal distribution. Looks something like this. What percentage of students are shorter than 1.5? The average height of the class is 1.6. So let me just draw it. 1.6. Standard deviation is 0.06. So plus 1 standard deviation will be 1.66. 2 standard deviation will be 1.72. 3 will be 1.78. Minus 1 standard deviation will be 1.54. 2 will be 1.48. 3 will be 1.42. That means this is basically your plus minus 3 standard deviation, which should have 99.7% data. This is plus minus 1 standard deviation. This is plus minus 2 standard deviation. Now talking about this question, what percent of the students are shorter than 1.5 mm? Where does 1.5 mm falls? 1.5 mm is somewhere here. That means I need to find how much percentage is beyond this particular line, right? Everybody is clear? So the first thing that we were going to perform is calculating the Z score. So again, we will take the help of the formula Z equals to x minus mu by sigma. At 1.5, we are going to calculate the Z score. So 1.5 minus 1.6 divided by 0.6, which is 0.1 minus 0.1 divided by 0.6, which is going to be 1.5 minus 1.6 divided by 0.06, which is minus 1.67. Minus 1.67. Clear? So the Z score at 1.5 meters is minus 1.67. Now look up the probability form, the Z score table. You can see minus 1.67. 0, 1, 2, 3, 4, 5, 6, 7. So this is the value. If I take this value, it is, sorry, my bad, it is 0.0475. If you multiply it with 100, that becomes 4.75%. That means 4.75% of the people, of the students, are shorter than the range of 1.5 meters. And that is how you use your Z table or your Z score table to identify such kind of problem solutions. That's all about this particular video. In the next video, we shall be talking about various other things. See you in the next video. Bye bye.